Hello everyone. The title of this video is Using the Fundamental Theorem of Algebra. So each example I'm going to be doing in this video is taken directly from a free online textbook at openstacks.org. I'm in their Algebra and Trigonometry text, section 5.5, called Zeros of Polynomial Functions, and I'm under the heading Using the Fundamental Theorem of Algebra. Each example I do will either be an example from the reading or one of the try it problems from the reading, or one of the exercises at the end of the section that's related to this particular objective. Okay, so first I want to go over, what is this fundamental theorem of algebra they speak of? Well, they say it here in words. The fundamental theorem of algebra tells us that every polynomial function has at least one complex zero. Right, complex, right? So remember, every number we have is complex. All the reals, all the imaginaries, any combination of them, right? Everything's complex. So every polynomial function has at least one complex zero. And they state it again down here a little more in depth. So the fundamental theorem of algebra states that if f of x is a polynomial of degree n, then f of x has at least one complex zero. And then you can extend this, right? This is called a corollary to the fundamental theorem of algebra. We can use this theorem to argue that if f of x is a polynomial of degree n, and a is a non-zero real number, then f of x has exactly n linear factors. F of x equals a times x minus c1 times x minus c2 all the way down to x minus cn, where c1 through cn are the complex roots, or the complex zeros of the polynomial. Right? So basically, what this part is saying is that if you're given a polynomial function, you should be able to write it this way if you know all the zeros. As a, which is going to be the lead coefficient, right? This a is just the lead coefficient of the polynomial. And then you have x minus a number, x minus a number, x minus a number, and all these numbers are just the zeros, the complex zeros of the polynomial. And if it's degree n, there will be n of these. Should have n complex zeros. Right? So that's the fundamental theorem of algebra, and this is what I'm going to be doing with all the polynomials we see. I'll show you how to express it factored this way as a product of n linear factors and some number, some lead coefficient. Alright, so that's all we're asked to do. Is I'm going to be given a function, right, a polynomial function. I'm asked to find all the complex zeros. Well, I have already done this in previous videos. I just didn't call it this. Right. I'm assuming that you know the rational zero theorem. So if you don't, go back and look this up, right? Know the rational zero theorem, please, before continuing on watching this. Because this is going to be used extensively in finding the zeros of a polynomial function. Alright, now, so I see f of x here equals 3x cubed plus 9x squared plus x plus 3. It's a polynomial function, and I'm asked to find all the complex zeros, all the numbers that I can plug x in to make this equal 0, right, to give me an output of 0. Now, one thing I'm noticing here, and you may notice this as well sometimes, just sometimes though, this polynomial is factorable by grouping. The first two terms have a common factor of 3x squared. and then you'd have x plus 3 left over. Plus, and then the second two terms have a common factor of 1, and it's just 1 times x plus 3. And then both these products here have a common factor of x plus 3. Let's have x plus 3 pulled out, and then the other factor remaining would be 3x squared plus 1. And again, we're trying to figure out, where is f of x equal to 0? And you may recall, the zero product property. If I have a product now, and I'm setting it equal to 0, then one of the factors has to be 0. So either when x plus 3 equals 0, or when 3x squared plus 1 equals 0. And we solve each of these. So one of the zeros is x equals negative 3. And then this one here, if you get the square alone, or you could use the quadratic formula, right? It is a quadratic. But if you get the square alone, you get x squared equals negative 1/3. So x must be, positive or negative. The square root of a negative number, remember, is imaginary. That'd be the square root of 1/3 times I. Remember how you write square roots of negative numbers using the imaginary unit I. And if we rationalize this, it'll be square root of 3/3. So the zeros of this polynomial are x equals negative 3. That's a real number. X equals positive, square root of 3 divided by 3. That's, after rationalizing, multiplying the top and bottom by square root of 3 here, times I. There's an imaginary number, right? And another imaginary 0, negative that, right? Negative square root of 3 divided by 3 times I. Now you can check them by plugging them in. You can check by plugging them in. And remember that I cubed would be negative I, and I squared would be negative 1. Right? Remember how to simplify powers of I. So yeah, if you were to plug any of these in, the output should be 0. Now, because there's only one real one, right, that's the only real number here, x equals negative 3, there's only going to be one x-intercept of the graph of this function if you were looking at the graph, right? Because remember, the x-axis is real numbers, right? So the imaginary zeros aren't going to show up on the graph, unfortunately. All right, but let's take a look at that too. I'm gonna probably take a look at all these. Right? Go to that Desmos website. It's a free online graphing calculator site, desmos.com. And I'm entering the function we were given, f of x equals 3x cubed plus 9x squared plus x plus 3. And you see it's only crossing the x-axis at one point, and that was at negative 3, as we said. And it doesn't have any other x-intercepts, right? So that means it has the one real x-intercept and two intercepts with an imaginary part, because again, it's degree 3, right? If it's degree 3, it should have 3 complex zeros, and only one of them is real, so the other ones have to have an imaginary, as we've already shown, right? We've already shown this. And again, you can check this yourself, plug these in, simplify. You will end up with 0 for all 3 of these, I promise you, but I'll leave that to you. Now, this means we can express f of x in the following way. Remember that second part of the fundamental theorem with the factored version of a polynomial? So that means I can express this function here in this way, as 3, right? That's just the lead coefficient, right? The leading coefficient was 3, and that's this numerical factor. Just the leading coefficient. And then since it's degree 3, I should be able to multiply this by 3 linear factors. where each one of them is just x minus one of these zeros. So x minus negative 3 times x minus the square root of 3 over 3 times I times then x plus or minus, negative square root of 3 over 3 times I. Right? That's what that meant. Once you know all the zeros and you also know the leading coefficient, you should be able to express any polynomial function as that leading coefficient times, a bunch of linear factors, x minus each zero. So we have f of x equals 3 times x plus 3, right, times x minus the square root of 3 over 3 times I times x plus the square root of 3 over 3 times I. And if you would like to check this, please do. If you were to multiply this out, so multiply these two here. If you multiply these two here, you'd get x squared plus 1/3, and then times the 3 would be 3x squared plus 1, and then 3x squared plus 1 times x plus 3 would give me, the original back like I showed you over here. All right? But you should be able to do this. Or express any polynomial like this once you know all the complex zeros. And if you want to check it, multiply it out, make sure you get the original polynomial back. Hopefully you remember how to simplify powers of I, right? Now, this particular one was factorable by grouping, right? So I didn't really need to use the rational zero theorem at all. You could, use the rational zero theorem, to make a list of possible rational zeros, factors of the constant divided by factors of the lead coefficient. And then you start plugging in those values from that list, and eventually you would have seen that negative 3 is a 0, and then you could use it to factor it, and you would have factored it exactly this way, x plus 3 times 3x squared plus 1, and then you find the zeros of all these, and you would have ended up with the same stuff. All right, but I just noticed that was factorable by grouping, so I was like, all right, I'm just going to do that because that's easier. But not every single the polynomials we see all the time are not going to be always factorable by grouping, like this next one. So same thing, find all the complex zeros of this polynomial, another degree 3. And you're like, yeah, it's got 4 terms, let me try grouping. Well, you're not going to be able to do this one by grouping, unfortunately. But I do notice, right, all the coefficients are integers. And remember, all the coefficients have to be integers to be able to apply the rational zeros theorem, right? Now, for the rest of the video, I'm going to be abbreviating the rational zero theorem as RZT. But by the rational zero theorem, any rational zero of this polynomial, if it has any, right? If it has any. It might not even have any rational zeros. But any rational zero of this polynomial will have to look like the following, right? We'll have to take the following form. X equals, and then you have a rational number, integer over integer. The numerator has to be a factor, some factor of the constant term, right? So some factor of 4. And the denominator has to be some factor of the lead coefficient, which is 2. And then over here I'll put in, what are the possible numerators then? The factors of 4 are positive or negative 1, positive or negative 2, and positive or negative 4. And since I have the negatives up here, I don't need them down here. The only factors of 2 then are 1 and 2. So I can use this to make a list. I'm going to make a list of all possible rational zeros of this function. and just the rational zeros, using all the combinations of numerators and denominators here. So positive or negative 1, positive or negative 1/2, 1/2. Positive or negative 2, and then 2/2 is just 1. I don't need to write that again. And then positive or negative 4, and then 4/2 is 2. Don't need to write that again. So here, now, it's a degree 3 polynomial, so it has 3 complex zeros. So, not all these numbers are going to work. Right? It can't have 8 different zeros. It's only a degree 3. So we start checking, right, and seeing, are any of these actually a 0? Now, if none of them work, then you're in a bit of trouble. One of these should work. If they're actually asking us about this right now, one of these should work, should be a 0. Because if it has no rational zeros, then we have to go into some more advanced methods that are beyond the scope of this course and this textbook at the moment. So I don't think we're going to, I think one of these should work. Right? And in fact, I think x equals 1 works. So let's check these. Now I like checking them. Now you can just plug it in if you want, but I like checking with synthetic division. And again, you've seen me do this in previous videos if you've been watching. So up top, the coefficients of the polynomial, 2x cubed, positive 5x squared, negative 11x, and then positive 4 for the constant term. Let's plug in 1. Remember how synthetic division goes. You drop down the lead coefficient, then you multiply, add, right, all the way to the end. 1 times 2 is 2, 2 plus 5 is 7. 1 times 7 is 7, plus negative 11 is negative 4. 1 times negative 4 is negative 4 plus 4 is 0, right? And so this is telling me here that f of 1 equals 0. Hooray! All right, so x equals 1 is a 0. And I brought this up in previous videos as well. Once you find a 0, you can then factor the polynomial, right? So f of x is equal to, 1 is a 0, so x minus 1 is a factor. And then these numbers in between here are the coefficients of the quotient, which would be another factor. And this would be a 2, it's in descending order, so it would have to be a degree 2, 2x squared, plus 7x minus 4. And then we kind of go to this quotient here and start again, find the zeros of this. Now, it is a degree 2 polynomial, so finding the zeros should be really simple. You can either try factoring it, or you can just use the quadratic formula. Now, this is factorable though, right? 2 times negative 4 is negative 8, and 8 and negative 1 add up to 7. Those are factors of negative 8 that add up to 7. So this is actually factorable. So I can keep factoring here. X minus 1 times, and then this factors to 2x and x, and I would need plus 4 here and minus 1 here. Right? So x minus 1 times 2x minus 1 times x plus 4, that's that polynomial completely factored. And, now that I have all the factors written like this, I can easily state the zeros. All right, what makes each factor 0? All right, so the zeros are x equals 1, as we said earlier. What makes, 2x minus 1 equals 0? That'd be x equals a half. And then x plus 4, that would be made 0 by x equals negative 4. And that's it. Here are all the zeros, and there are 3 of them. This degree 3, there should have been 3 of them, of that polynomial function. Then we can say that f of x equals, the lead coefficient, which was 2, right, times, and then, 3 factors with x minus each of these. X minus 1 times x minus a half times x plus 4. Now, do you see how these are the same? I got the x minus 1 factor, got the x plus 4 factor, all I did was basically take 2x minus 1 and factor out a 2. All right, 2 times x minus a half would be 2x minus 1. So they're the same thing. And that's it. That's all we were asked to do. Now let's double check it. All right, let's look at a graph of this thing. And notice that these are all real numbers here, so they should represent where the graph crosses the x-axis at 1, 1/2, and -4. And let's check that out. All right, so we're given f of x equals 2x cubed plus 5x squared minus 11x plus 4. And you see the 3x intercepts, right? -4, we said that was 1. Positive 1/2, that was one we had as well. And positive 1. All three of them are the exact same 3 I had here. Excellent. All right, let's do it again. Now this is a little different, but it's pretty much the same kind of problem. They're giving us an equation here, some polynomial equals 0. This is exactly the same as find the zeros of this polynomial function of, say, f of x equals x cubed plus x squared, plus x plus 1. Anytime you have an equation where you have an expression equal to 0, you're just finding the zeros of some function. Right? What inputs give me an output of 0, something equal to 0. All right, so once again, now all the coefficients are integers, so I could use the rational zero theorem, but once again, lucky me, I'm pulling these directly from the book, so you're just as lucky as I am when you work through the book problems. You can use the rational zeros theorem if you wish to make a list of possible rational zeros. Now, I mean, the possible rational, I'll just put RZT here. The possible rational zeros are just positive or -1, factors of 1 divided by factors of 1. And I'm hoping it's obvious that 1 doesn't work, because you just have 4 here. All the signs are positive, so plugging in a positive number is not going to work. Not going to make it 0. So -1's got to work here. So I got 1x cubed, 1x squared, 1, 1. All the coefficients are 1, but -1's got to be the one that works. Drop the 1. -1 plus 1 is 0. 0 plus 1 is 1. -1 plus 1 is 0. And so we're seeing that f of -1 is 0 when I called f this polynomial. So I can very easily factor this now. This factors to x plus 1 times, and then these give me the coefficients of, the quotient x squared plus 1. And we have this set equal to 0 here. Now, when I said I was lucky earlier, this is also factorable by grouping. Right? The first two terms, if you pull out x squared, you'd have x squared times x plus 1. And then the second two terms have a common factor of 1, also times x plus 1. And then you can factor out the x plus 1 from both those and leave you with the other factor of x squared plus 1. So I get the exact same thing, right, when I factor it by grouping. But that's not always possible, so I'm not going to, let's say we didn't do that. Alright, so now I just want to find the zeros of this. What are the zeros of x squared plus 1? So off to the side here, when is x squared plus 1 equal to 0? Well, that's when x squared equals -1 and square root both sides. That's when x equals positive or negative I. Right? Remember the square root of -1 is that imaginary number I. I know I should have written that earlier, but remember that I. So there we go. There's all the zeros. X equals -1, which is a real number, and then we have two zeros with an imaginary part. X equals 1i and x equals negative 1i. And you can check all these. I'll leave it to you. Replace x with negative 1 with I with negative I back in the equation, and you should get 0 equals 0. Alright, yeah. And then knowing all this means we could write f of x the following way. We could write this polynomial x cubed plus x squared plus x plus 1 this way. Now the lead coefficient is 1, so I don't need to write that, a factor of 1. And then just times x minus, 3 factors, just degree 3, 3 factors, each one has x minus 1 of these, so x plus 1 times x minus I times x minus negative I, or x plus I. And there's another way to express that polynomial, right? And if you were to multiply these out and combine like terms, do all the multiplication and like term combining, you'd end up with x cubed plus x squared plus x plus 1. You should, and again, I'll leave that to you. You should know how to multiply polynomials anyway. All right, and then once again, the only real solution here was negative 1. It's two imaginaries. So if I were looking at the graph of this polynomial function, it would only hit the x-axis at one place, at negative 1. And let me just check that. So the polynomial function here, x cubed, y equals x cubed, plus x squared, plus x plus 1. And you see how the graph, zooming out, whatever, it only hits the x-axis at one point, and that's this point here at x equals negative 1. Right, that was our only real 0. Right, and we're seeing that in the graph. We're seeing that here. All right. Great. All right, let's do that again. All right, so here, another degree 3 equation, polynomial equation. And once again, solving this equation is exactly the same as finding the zeros of this polynomial function. If you had f of x equals x cubed plus 13x squared plus 57x plus 85, it'd be the exact same thing as finding the zeros of that. All right, what input of x gives me an output of 0, equal to 0 here. Okay, so here, I'd say this one's not factorable by grouping. So I notice all the coefficients are integers. So I can use apply the rational zero theorem, RZT. And, the lead coefficient's 1. Right? So the only numbers that are possible rational zeros here are the factors of 85. So I'm just going to write to the list, So plus or minus 1, plus or minus 85, right? 1 times 85. Let's see, 2, 3, no. 5 obviously goes into it, ends in 5. So plus or minus 5, and plus or minus 17, and I believe that's all, because that's just 5 times 17, and those are prime. Okay, so 4 numbers to check. Now here's the nice thing though. Sorry, 8 numbers to check, but really there's only 4 numbers to check. This is just an observation I'm making. See how all the coefficients are positive? So a positive number is not going to work here. I'll just write that off to the side. Now, since all coefficients are positive, a positive number will not be a 0. Because that'll just make everything more positive. You're not going to add up to 0 if that's the case. So a positive number will not be a 0. So that cuts my list in half. So when I go to check these with synthetic division, where we got 1x cubed, 13x squared, 57x to the first, and then 85. I'm going straight to the negative numbers first, right? So how about negative 1? Drop the 1. Negative 1 plus 13 is 12. Then negative 12 plus 57 is 45. And then negative 45 plus 85 is 40. So negative 1 is not a solution, is not a 0. Alright, now I'm going to jump to the next lowest. We'll save negative 17 and 85 for later. Negative 5. I'll do negative 5 next. So drop the 1. Then negative 5 plus 13 is 8. Then negative 40 plus 57 is 17. And then, negative 85 plus 85 is 0. Hooray. So I can use this to factor the polynomial, right? This degree 3 polynomial now factors to x plus 5, right, since negative 5 is a 0, times, and then these numbers here represent a degree 2, x squared plus 8x plus 17, which is not factorable. So now I'm trying to find the zeros of this degree 2. So when it is off to the side here, when is x squared plus 8x plus 17 equal to 0? Now if you can use the quadratic formula, or you can do complete the square, right? X squared plus 8x plus, half of this is 4 squared is 16 equals, and then I'd subtract 17. Negative 17 plus 16 is negative 1. And then this is x plus 4 squared equals negative 1. So x plus 4 is equal to positive or negative I, right? The square root of negative 1. So again, we're getting two solutions with an imaginary number in it. So x equals negative 4 plus I and negative 4 minus I. And there are the zeros. All right, so degree 3 polynomial. I have found all three complex zeros. X equals negative 5. That's a real number. And so that's where the graph of that function would cross the x-axis. And then we have x equals negative 4 minus I, or plus I, and then negative 4 minus I. There we go. That's what they want. Now if I were to write this in some sort of factored form, right, x cubed plus 13x squared plus 57x plus 85, I could write as 1 times x plus 5 times x minus the quantity negative 4 plus I times x minus the quantity negative 4 minus I. And there we go. Right, this is like I was doing in all the other problems, right? Everything is x minus some complex 0. Or x plus 5 times, and then if you actually distribute the negatives here, this factor would be x plus 4 minus I times x plus 4 plus I. Right? And there's a way to factor the polynomial completely over the complex numbers. And once again, you want to check it. Multiply these two, then take that result. Now, when you multiply x plus 4 minus I times x plus 4 plus I, you should get x squared plus 8x plus 17. And then you multiply by x plus 5, and you'd get x cubed plus 13x squared plus 57x plus 85. You should. And I'll leave it to you to check that. All right, and once again, it only has one real solution, one real 0. So if I were to graph this polynomial function, it should only cross the x-axis at negative 5 and have no other x-intercepts, right? Because the other two zeros have an imaginary number in them. All right, so let's check that. Double check it, see if it actually crosses at negative 5. So x cubed plus 13x squared plus 57x plus 85. And yeah, you can zoom out as far as you want. You're only seeing this one point here where the graph crosses the x-axis, and that's at negative 5, like I stated earlier on my paper. All right. So, looks good. All right, and I've got just one more example, but this time it's a degree 4 polynomial equation. Again, everything on one side, 0 on the other, so solving this equation is just like finding the zeros of this polynomial function. Now, the only thing about having a higher degree, right, the higher the degree, the more tedious it gets. You just have to repeat the same steps over and over. All right, if it was a degree 5, I'd do it 3 times over. Degree 4, you're going to see them do the same thing twice. So I can't really think of how to factor this in some other method, right, grouping or whatever. So I also notice, all the coefficients are integers. So I can apply the rational zeros theorem to make a list of possible rational zeros. Now, again, the lead coefficient is 1. So that list of possible rational zeros is only going to be made up of the factors of negative 75. So numbers that go into 75 evenly. So positive or negative 1, positive or negative 75, right? 1 times 75. And then positive or negative 5. Well, actually 3 and 25. Right, 3 times 25. And 5 times 15, right? Positive or negative 5, positive or negative 15, and I think that's it. 3 times 5 times 5, yeah. Okay, so if this has any rational solutions, it's going to be on this list. Alright, so let's start checking. Oh, we're very lucky. X equals 1 works. Start checking here. We got 1x to the 4th, 2x cubed, 22x squared, 50x to the 1st, and then negative 75 for the constant term. 1 works. Watch. Drop the 1. 1 times 1 is 1, plus 2 is 3. 3 plus 22 is 25. 25 plus 50 is 75. And then 75 plus negative 75 is 0. Oh, we are actually very, very fortunate here. So we can factor that polynomial to x minus 1, and then these give me a degree 3, right? There's 4 of them. It's in descending order. It would have to be a degree 3 polynomial. 1x cubed plus 3x squared plus 25x plus 75. And now we're finding the zeros of this degree 3, right? That's what I meant by repetitive. So you kind of start over, right? Now notice all the coefficients of this are integers, so I can use the rational zeros theorem. But wouldn't it be the same list? You're checking the same list, because this is factors of 75, all right, divided by factors of 1, the lead coefficient of that x cubed there. And so off to the side, let's do it here. We'll check those numbers. So I have 1x cubed, 3x squared, 25x, and 75 is the constant term. Now, 1 was a 0 earlier. It can be a 0 again of another factor, right? Zeros can have multiplicities higher than 1. So just because I checked 1 earlier and it worked doesn't mean it can't work again. So I'm going to start now. I probably shouldn't check 1 though. Look at all the coefficients of this degree 3. 1, 3, 25, 75. They're all positive. Positive 1, positive 3, positive 25, positive 75. So a positive number isn't going to work. So I guess I won't check 1 again. But just know that you could, right? Know that a number can be a 0 more than once. Just understand that. I'll check the negatives though, right? So we're going to check basically same list, but not positives, right? Not the positives. They won't work because all the coefficients are positive. So drop the 1, then negative 1 plus 3 is 2. Negative 2 plus 25 is 23, and then negative, now this isn't working. I'm just going to put no. Now I already know that negative 3 works. Negative 1 didn't work. Negative 3 works. Drop the 1. Negative 3 plus 3 is 0. 0 plus 25 is 25, and then you have negative 75 plus 75 is 0. All right, so now I can factor this even further. We have x minus 1 from earlier. And now we have x minus negative 3 or x plus 3. And then these numbers here give me a quadratic, x squared plus 25. And now we start over, find the zeros of this. Now the reason I said we were lucky earlier is because this degree 3 can be factored by grouping. So I'll leave it to you to see how. If you remember, I've done factoring by grouping a couple times on this. So you didn't have to use the rational zeros theorem here. You could have factored this by grouping and got x plus 3 times x squared plus 25 eventually. Alright, so when is x squared plus 25 equal to 0 now? You can use the quadratic formula, or this is when x squared equals negative 25. So when x equals positive or negative square root of negative 25. Now remember, the square root of a negative is imaginary. The square root of negative 25 is the square root of 25, which is 5, times I. So positive 5I, negative 5I. And now I have all the zeros. All right, all the zeros. The zeros are x equals 1, x equals negative 3, and then from this last factor here we have 5I and negative 5I. X equals 5I, x equals negative 5I. And there we go. Right. Sorry, that's off the screen there. I apologize. And if you were to totally fully factor, it would factor this way. X minus 1 times x plus 3. And then this x squared plus 25 can factor to x minus 5I times x plus 5I. Right. And this is like the polynomial completely factored over the complex numbers. Right. And again, the lead coefficient was 1, so there's no need to write a number in front of this. It's just 1. Right, and also just to double check, notice how there are 2 real number solutions here, 1 and negative 3. So the graph should have those as x-intercepts, right, the graph of this function. And then the other 2 intercepts have an imaginary number in them, so you're not going to see those on a graph, right, because the x-axis is, again, a real number line. So this polynomial was x to the 4th plus 2x cubed plus 22x squared plus 50x minus 75. And you see, now again, I can zoom out a bunch, and you're only going to be seeing those 2 points on the x-axis. All right, and those are at negative 3 and positive 1. Exactly like what we said back here. All right. So yeah, so it's the same procedure pretty much every time. You noticed, I hope. Make sure the polynomial you're looking at has integer coefficients. Now, if there's some fractions, just multiply by the least common denominator to change all the coefficients into integers. Right? Because multiplying a function by a number just causes a vertical stretch or compression, but that doesn't actually change the zeros. It doesn't change the x-intercepts. You may remember that from function transformations. So make sure your polynomial has all integer coefficients. Then you can apply the rational zero theorem to make a list of possible rational zeros, like here, like I'm pointing at. Then you check that list, and once you find a 0, you can factor to a degree 1 times a degree n minus 1, 1 less, and then you take that quotient and start over if you need to. Now, if the quotient's a degree 2, you can stop. You should be able to know how to find the zeros of a degree 2. You can either use the quadratic formula, complete the square method, or try factoring it if it's factorable over the integers. And then, once you get down to degree 1 and degree 2 factors, you should be able to find all the zeros. It can just be a tedious process sometimes, as you've noticed. And that's it. So I'm hoping that watching me go through these 5 examples in this video help you in some way when you're asked to find the zeros of a polynomial function, and then use the fundamental theorem of algebra, or at least that corollary, to be able to factor it like I've been doing, where all the factor, you have some lead coefficient times, and then all these factors where you have x minus one of the zeros, right, and all for all the complex zeros. thank you very much for watching.